Okay, so this is a summary of what we studied until yesterday. We said a quantifier, a predicate could have more than one variable, 2, 3, 4, as many as you want. And each variable needs to be given a value or quantified so that it becomes a predicate, a proposition. And then we can say whether it's equal, true or false, or whether it's equal to another proposition or something. Okay, and we discussed that when there are different quantifiers for different variables, then the order of those quantifiers is extremely important, right? The meaning of the sentence changes just totally if you change the quantifiers, the order of the quantifiers. But if they're the same quantifier, then you can switch the order, right? So, and this is a summary of when a quantified statement is true and when is it false, and that's how you will make. It will help you translate statements into math and English. Let me ask a few questions from you so that we just finish a few entries of this table. When is for all x for all y, p of xy? That's a predicate with two variables, and both variables are quantified with the universal quantifier. So the first thing you should note is that I've written both of them in one row of the table. That means they are equal, right? They're the same thing. You can switch the quantifier order. When is for all x for all y, p of xy true? Quickly.
Then p of xy is true for every pair xy.
For every pair xy, x comes from a universe of discourse, y come from perhaps a different universe of discourse. But for every pair in one universe of one element in one universe of discourse and other element in the other universe of discourse could be the same. For every pair, if pxy is true, then it is not true, right? And then it is true. And when is it false?
Then there is a pair xy for which pxy is false.
If there is even only one pair for which pxy is not true, then the statement is false, right? It may be true for all x's except one. And for all x's and all y's, right, except for one x value, fixed value of x and one fixed value of y. So for all this, for all others it may be true. But even if there is just one example of among these the cross product of these universes of discourses, then universes of discourse, then this is not going to, it's going to be false, right? Similarly, there exists x, there exists y, and there exists y, there exists x. This order you can flip pxy. When is it true? When is there exist x, y, there exists y, pxy true? Yes, please. So if x has 100 elements or 10 elements and y has the universe of discourse of x has 10 elements and universe of discourse for y has 12 elements. So out of this total 120 possible pairs, even if there is one pair for which pxy is true, this statement is true. And when is it false? When is it false? Yes. It's okay, say it. Here it's not a sin to say something even if I didn't ask you. How many? So in this case, there are 10 pairs, 10 x possible values of x's and 12 possible values of y. If it is false for all of these, every one of these 120 pairs. Yes?
Does this statement mean that there exists an x for every y to make it true to all pairs?
There exists an x for every y. No, that is actually the statement. There exists an x for every y. Right? There exists such an x. There exists an x such that for every y, this fixed x or at least one x works for all y. Right? If you picture this let me just draw it. The universe of discourse, the pairs of universe of discourse could be written like this. So this is possible values of x. We said this is 10 of them. And these are possible values of y. We said there are about 12 of them. Right? Okay, so for all x, for all y, says that if I plug in this xi and yj value, this is true for any value of, in every row, in every column, this matrix is full of true statements. This is clear? So this statement is a proposition. The value of the predicate when x is equal to xi and y is equal to yj. Right? So all of these propositions are true. That is this statement. This makes sense? Yes? What is this statement? There exists x, there exists y. There exists, says that out of these 120 propositions, at least one is true. So there is a true statement among these 120 in this matrix. Does that make sense? What would be this statement? For all x, there exists a y. So what is this statement? In every row, row x correspond to rows, and so what does this say? Can you like really say it in really plain, simple language? Out of these 120 propositions, what does this say?
Every row has a 1.
Every row has a 1. Yes. There is at least one true proposition in every row. Does it make sense? Yes, because in every row, there exists an entry y, an index y, such that that row, the proposition at that row and this y is, that row and this column is 1, right? So there exists at least one column, at least in every row, there is at least one true proposition. Is it clear? And what would be this statement? Now this is not the same as this, okay? These we can write this way also. But this is like grammatically incorrect thing because there is a pxy there, right? But you know what do I mean by this? What is this statement in terms of this table or matrix? There exists a y, x, there exists an x such that for all y, what is that? Yes, please. True proposition in every column? No, you cannot talk about a proposition unless you specify both row and columns, right? Because there are 120 of them arranged in a particular way. There is at least one true in every column? Not really. Yeah. Yes, please. Yes.
One row.
Yeah, go ahead.
There is at least one row which has all the true values.
Yeah. Can you say it? What was your answer?
There is at least one row in which every column.
Yeah, so there is at least one row, fix x, there is at least one row, such that for every column, I get a, in every column of that row, I get a true statement, right? So it's like there is a row of all true propositions. Yes? Yes, please.
So here we're saying that the x is the same for all y's.
What is the same?
The x is the same
So there is one x.
for the same x.
Yeah, there is one x for which all y's give me this thing.
We say that in the previous example that there should be the same y for which all x is.
There should be the same y. So no, the way I statement, for every x there is a y. Right? For all x there is a y. So that doesn't mean that there is a y for all x. So every x could have a different y. Does that make sense? Okay. So if that helps you, do it that way. If English or this type of things, just think about it this way. Okay. It seems like this matrix is not really complete. Yeah, so there should be two more rows. There exists y for all x because order of quantifier is, so there should be two more rows here. One is there exists x, there exists y for all x, right? But you have to think about it, x and y are just dummy variables, right? So all the language except for now we got a statement where there is a row full of true statements, right? True proposition. Then it will be there is a column full of true propositions, right? True statements. So maybe you should add that if you want. Okay, so just some quick examples because these are your ICPs and we couldn't complete it. If I want to make this statement, at least one console must be accessible during every fault condition. Okay, so this is the system testing, specification, right? Typically this happens when people do software testing or other system testing. So these kind of statements are made, and that's why it's copied from that literature somewhere. So how would you make the statement? What will be the universe of discourse for these console and for fault condition? So when we're talking about for each fault condition or for some fault condition, this will be the universe of discourse will be the set of all possible faults or the set of faults observed or expected or possible in the system. Okay, and console will be whatever types of console we are talking about, right? That will be the universe of discourse. How would you make this statement? At least one console must be accessible during every fault condition. Now again, it's a tricky business, okay? That's why we spend quite a lot of time in there, and this is where the whole purpose of this thing is. Now onward, when you make a statement, there would be a precise meaning of it, right? Not like this. So suppose there are 3 fault conditions: fault 1, fault 2, fault 3, F1, F2, F3, okay? And there are 5 consoles: C1, C2, C3, C4, C5, okay? And think about it. So does this say that for F1 there should be a console, it is available, or for F2 the same console should be available, for F3 that same console should be available, at least one console is going to be available, right? So how would you say this, do this kind of analysis, just like English to English translation to make life easier, and then translate it? Yes, please.
For every fault condition there exists a console such that whatever the property is true.
Yeah, so for every fault condition, there is a console that must be accessible. That's what his answer is. Any other answer? Any other try? Yes.
There exists a console for all fault.
That's a very good attempt. There exists a console which is accessible during every fault condition, right? Which one do you think? Does everyone understand that there are difference between these two statements, right? For every fault condition, there is a console available, right? That's one way to write it. The other way is there is a console that is available for every fault condition, right? You see the order of quantifier? Yes, please.
So second वाली का ये मतलब है कि एक console universal है, हर किसी के लिए चल रहा है.
That's true. That's a correct interpretation of the second one thing. Is it a correct answer to this question? That's my thing. But do you understand the difference between the two, right? And that's the trick here, and that's what it is. So this says, if you look at every fault condition, right? Fault type 1, maybe console 7 is available for fault 1. For fault 3, fault 2, console number 19 is available. For fault 3, console number 1 is available. For fault 4, console number 4 is available. That would satisfy this thing. At least one console must be accessible. If a fault happens, I should be able to, this is a system testing thing, right? The tester or the administrator should be able to access at least one console to administer the fault. Yes? So that would basically mean that for all y is perhaps your fault conditions, right? You see it says fault condition y. So this requires that for each type of fault there is a fixed computer that is available, that is accessible. That's not what is meant there. What is meant is if a fault occurs, I should have a console available. It doesn't have to be the same for every fault. Okay? Again, that's the problem with English language, right? we make, so I know what is true because of some context, because of my language skills, and because of the context, because of my domain expertise, because of who my audience, and there are many other things, right? But now once you know this stuff, when you write it like this, then there cannot be any dual interpretation. Now if there is a dual interpretation from here to English, that's your fault. Okay, that's my misunderstanding of the math language. Okay, yes please.
But see that we are given the English statement, we can interpret.
No, we cannot. This one you cannot. At least one console must be accessible during every fault condition.
Just like there is at least one console that is available to all parties.
Yeah, so if you say it, that's a different statement, you have to say it differently. I think that is what the interpretation is of this English sentence, and that is actually, again, maybe I'm using a lot of context, or I'm using a lot of some domain knowledge. Yes, please. So she says if we switch the order of these existential quantifiers, so there exists x come before and for all y goes later, right? And then axy is just a shorthand for x is accessible during y. The meaning will change totally differently, right? The meaning will become differently. Again, if you think of it as this, in this form, suppose the rows are false and the columns are consoles. Then if you change it, so this says there exists a y, there exists an x. That's what he said, right? There exists an x. So there exists a row such that for all y, for all column, there is a 1 there, right? So there is a row full of true statements, accessible thing. Let's just do the say, forget about fault condition in x and y. So there is axy. Suppose these axy's are written here. These are possible x's. And these are possible values of y's, and this is the value of the proposition when I plug in the ith value for x and the jth value for y. Okay, so now it's either true or false. So this statement says that there exists a row such that for all y's, it's a true statement, right? So this says there exists some row, maybe the 19th row, which is all true statements. It's a different statement. But if I say this thing, this is what he said, for all y there exists x. For all y there exists x, right? Some x such that axy is true or 1, right? What is this? In every column there is one row which is a true proposition, right? So suppose in this row, this is that one condition. Suppose here is in this row, the first one is 1. In this column also the first one is 1. In this column this one is 1. And in this column this one is 1, and so on, right? But in every column there is at least 1, 1. This is a totally different statement. This says in every column there is a 1 somewhere. Not exactly the same level, at the same height or same row. This one says there exists a column that is full of 1. So it's a different statement, right? So you can never switch the order of quantifier when they are different quantifiers. Yes?
So regarding the same thing, then how would we say the English of the first one? Because if we read it in that context, it still makes sense.
So how would you say? That's a very good thing. So one of the best ways to translate English to logic expression is to do a couple of things. Translate from English to math, and then translate it back from math to English and see if it makes sense or not, right? To do these kind of case analysis, let's suppose I have the statement there exists an x such that for all y, axy, right? So the English translation will be there is one console that no matter what fault occurs, that console is available.
Which is also the same as for every one.
No, but I think you're missing this at least one, right? So there is one console, or there may at least one console, but it's available during all fault condition, right?
So it's all in every
that's the problem with this. That's what I think we began the first day of this course. We said that I am really amazed at how people actually communicate in English. This is in all natural languages, right? There are these issues. Okay. The email address of every user can be retrieved whenever the archive contained at least one message sent by every user on the system. Think about it, a little bit of quite a mouthful of quite wordy sentence, but let's see. The email address of every user can be retrieved whenever this condition is met, right? So let me just say R of y is the email of user y can be retrieved. Okay? Email of user y can be retrieved. So the first part of this sentence is for all y R of y. Right? For all y R of y. That means the email of every person y can be retrieved. Does this make sense? Now there is a condition for that. So there is something implies for all y R of y. Right? So just a second. Is this clear? You break down the English sentence, this whenever, whatever is before whenever, whatever is after whenever, and just do this basic thing, right? So this is what it says. I'll come to you. The next one says the archive can contain at least one message sent by every user on the system, right? So archive meaning there has been sent, right? So there is nothing called archive. I said mxy, x has sent, message x has been sent by user y. Right? Message x has been sent by user y. So just independent of the first part, this after the whenever part, can you say it in terms of mxy? X is a user's message and y is a user. For all y, there exists an x such that r of y. Such that? No, if forget about this, I'm talking about essentially the second line here. After whenever, at least one message has been sent by every user on the system. Just this part. Just, okay, if you want to complete your answer? Okay.
There exists an x for every y, m of x.
There exists an x for every y, mxy. Okay, so her answer is there exists x such that for all y, mxy. Yes?
For all y, there exists an x such that mxy.
mxy. So she says the opposite. She did the quantifier. She said for all y, there exists an x such that mxy. Okay? Is this clear? That sounds better. Look at this one says there is one fixed message, one email sent by all of them. That's not true, right? That's not really, that doesn't make any sense. An email is sent by one person from one address to another. But it says everybody has sent some message. Like no mailbox is just like born now, right? Or born today. There has been some activity from every account. That's what is meant by this, right? So we know the later part. We know the previous part, but you see at least a difference when I switch the quantifiers, things change, right? Now, what did you want to say?
I want to say,
You wanted to answer, okay.
for all y, ry, if there exists x for which mx.
Yeah, now generally we don't do if, no? If is generally comes before if x can. Okay, now can somebody complete the whole thing? Yes. Just please say it louder a little, you're sitting far away. What implies? No. There exists x for all y is not even a statement. Yes. Good, that's a good one, but we just said that there exists x for all y, mxy is not even the correct interpretation of the second part of the sentence. For all y, there exists x, mxy means everybody has sent at least one message. What you said is there is a message what has been sent by everyone. Yes. No, that's not the same. No, that's basically saying there is some message X, there is at least one message X that has been sent by all Y. That is a different statement than saying everybody has sent some message. Does this make sense? A message is sent by one person only, one email address. Sorry? On the board, yes. These are absolutely not equal. We spent the whole last lecture on it, and even this part of this lecture. They are not equal, okay? Look at this. Order of the quantifiers, if they are different, is extremely important. It makes the meaning totally different. I showed you this example. People carving pumpkins, pumpkin carving people. If you change the order, everything changes, okay? Okay, and we saw many other examples of this thing, right? Some course is being taught by all, or somebody teaches, some course is being taught by all, or everybody teaches some course. These are different statements, right? One makes sense, the other just doesn't make any sense. Okay, so here is the my translation of this. For all Y and for all Z. This is what you're mixing. The dummy variable X is a dummy variable, okay? It's this everybody, every user, and this every user is a different statement. This says, can I retrieve the email of Z? Let's say, can I retrieve the email address of Z? Can I retrieve the mailbox of Z? Well, if everybody has sent an email, then I can retrieve the email of Z. Right? Can I retrieve the email of Z too? Well, if everybody has sent an email, then I can. Right? If there is an unused mail address, then I cannot address the email address of Z. Z1, Z2, Z3, I cannot say it for everyone. Does it make sense? Okay? Yes, please.
So it can be do for all Y, R of Y implies there exists an X, M X Y.
No, this whenever is a condition.
So you're explaining what you brought in Z.
Okay, so suppose in the system, yes, please. Okay, so that's what I was going to say, that because you got engaged too much into the first part and the second part, which we I think hopefully learned all of us how would you do it. This statement is saying, suppose there is one user who is never touched, he never sent an email, right? Can you retrieve the email of Z? How? There is a user U19 who has not retrieved who has never sent any email. Can you retrieve the email of Z1? U19, U1, U2. We may not be able to do it, right? This statement doesn't talk about it. Okay? This statement says, I will be able to retrieve any email address if everybody has used their mailbox. Now, this any email address and everybody, this every email address and everybody doesn't have to be the same, right? That's where the Y and Z comes. Does it make sense? Yeah. X is, we think of X as standing for message, email ID. Y की जगह Z. No, वही user नहीं है ना. It does not say, if Z sent an email, then I can retrieve Z's address. It doesn't say this. It says I can retrieve Z's address if everybody has sent email. If everybody has used their mailbox, I can retrieve any email address. It doesn't require, the system, that's why it's verbose here, it says if all emails have been used, right, there is something called a dirty bit. If the dirty bit is set in all email, then I can retrieve any email address, right? If you just substitute, if you make Z and Y equal, right? So then for all z doesn't make sense, right? You just use for all z. So the meaning, if you retranslate it into English, if you replace here with z and you retranslate it, this would say, if z has sent an email, if z has sent any email, then I can retrieve z's address. That's not what the statement says, right? Yes, please.
तो जब हम LUMSx define कर रहे हैं तो उधर हमें LUMSz नहीं करना चाहिए do statement LUMSy.
These are just dummy variable names. These are just, you know, in C, when you write variable name for I equals 1 to k, for I equals 1 to n, you can write for p equals 1 to n. These are just things. But if I make them this z, let me just write this statement. Let me write this statement. Can everybody read this? Translate this statement into English. You know what is M, you what is R. Translate this into English quickly. For every user Y, the following is true. For every user Y, the following is true. If that user has sent any message, then I can retrieve that fixed user's email address. Email. This is what this statement says, right? Is it clear? Once you go inside this loop, y is fixed, right? The value of y is fixed. So you are saying for every user, for y1, suppose the value of y1 is true. If y1 has sent an email, then I can retrieve y1's address. This says, if y2 has sent an email, then I can retrieve y2's address. If y3 has sent an email, then I can retrieve y3's email address. That is what this statement is saying. If you didn't bring this z and y. Yes?
But sir, what would the universal discourse be?
So for y and z, it will be the set of users. For x, it will be the set of different types of emails or. Yes, we have two variables. In all of these predicates, we have at most two variables, right? So for each variable, we can have a universal discourse. So we have only two variables. Names are different. That's not important. Yeah. No, sir. This interpretation, so let me try my Urdu. This would be interpreted as the following. जिस यूजर ने ईमेल भेजा उस ईमेल का उस यूजर का ईमेल रिट्रीव कर सकते हैं. That is what this would mean. जिसने ईमेल भेजा उसका ईमेल रिट्रीव कर सकते हैं. This is not what this statement is saying. This statement says, अब सबने ईमेल भेजा फिर मैं किसी का भी ईमेल रिट्रीव कर सकता हूँ. Sorry, say it again. Why?
Why did we not put the for all y after the
After the for all z, that's, I told you, this is more technically correct, but this statement is totally independent of for all y. There is no y here, right? So you could bring y here, for all y here. That makes easier, that's more conveniently understood. But this is more technically correct. You first get rid of all the variables and their quantification and then write the statement. This is, I told you yesterday about Goldbach conjecture too. I don't think if and only if will be work this. No, because you may be able to retrieve some emails without even somebody not sending email. No, this is mentioned. This says it's if x then y means if x then y. It doesn't mean x not if x if and only if y. You can never confuse if and only if. That's very well understood. Yes.
If I want this just to way, that will still be okay, right?
If you want to say this with just two variables, you could perhaps, I don't know, maybe you can. So generally, what she suggested is, what if we write like this? Then this could be correct. These are just variable names, right? Doesn't matter. This y is now different than this y.
Sir, without the operator here, does it not mean even
No.
has been sent, some message X has been sent by user Y?
By if some message is sent by y, the email of that y can be retrieved. This is what this says. Because this y is fixed. Now you give a value to y. Now this is the same y you're talking about. Okay? So this translates is if y has, for every y, the following statement is true. If y has sent some message, then I can retrieve that y's address. This is true for any y.
How is that not okay considering we're
No, it may be okay. I don't care. That was not. This statement doesn't say it. So, can somebody say it in Urdu? Can you say it in Urdu? I said it, but this statement and this statement. I think I told you, but maybe that was wrong. Can you say this statement in Urdu? Or anyone else who want to give it a try, give it a good, easy translation?
किसी भी chosen by value के लिए कोई x exist करता होगा जिस
ना छोड़ो, that's even difficult. तुम्हारा उर्दू मेरे से भी बुरा है. Yes, can you say something? You don't say there exists and for all. Yes, please. Okay, let me just get my question answered and then yours will answer it. Can you say this one? Can you say this one in Urdu? Yes, board wala.
हर यूजर को तो क्या बोलेंगे हर यूजर के लिए
यार what is wrong with my translation? Okay, जिस यूजर ने ईमेल भेजा है, जिस यूजर ने कोई मैसेज भेजा है, उसका ईमेल रिट्रीव हो सकता है. Isn't that the correct translation of this? जिसने भी, that's will for all, right? जिस यूजर ने भी ईमेल भेजा है, उसका मैसेज भेजा है, कोई भी मैसेज एक्स, देन उसका ईमेल रिट्रीव हो सकता है. This is this statement, right? What this statement says, सबका ईमेल रिट्रीव हो सकता है, किसी का भी ईमेल रिट्रीव हो सकता है, अगर सब ने ईमेल भेजा हो, अगर सब ने कोई मैसेज किया हो. These are different statements, no, in Urdu? Are they different? In Urdu, are they different? Yeah. Okay, so you had questions, quickly. Okay, this one? Okay. So this says, for any user y and for any user z. Okay, for all users y and for all users z, if z has sent a message, some message, let's say there exists x, if z has sent some message, then the email of y can be retrieved. What is y? Any y, right? The first thing tells us any y. So forget about this statement. First say this statement from z, x and mxz. What does this mean? What does this mean? What does this means? Quickly say it.
Some message has been sent by.
Every user has sent some message. This is this part means, right? Before the implication and after for all y. Every user has sent some message. Is clear? For all y there exists x such that mxy, mxz. For all z there exists x such that mxz. That means every user has sent some message. If this is the case, if every user has sent some message, you could simplify your life a little bit like this. Sorry, there is I guess z there, right? So let me replace this. Look at this. Suppose I call it Q. This whole predicate is a quantified predicate, now it's a proposition. Right? Maybe true, maybe false, I call it Q. Right? That statement, the remaining statement says, for all y, Q implies R of y. Now what does Q stand for? Everybody has sent some message. That's what Q stands for, right? Everybody has sent some message. Now this one says, for any, so if everybody has sent some message, then email of everyone can be retrieved. Now this everyone comes from this for all y. Does it make sense? Yes.
So just for my own understanding, would it be smart to look at this as like a local property and that is a global?
I don't know. I generally get scared of big words and unknown words, so I won't use those words. Maybe it's true. I don't even know what a local and global property means.
Does it mean that there is a possibility that we can message भेजा, so we cannot retrieve any users?
No, that's not true. You are right. If there is one person who is so lazy, never sent an email, then this statement, then we cannot guarantee that anyone's email can be retrieved. Not necessarily that one idiot. Maybe others we could not, but we just don't know. Suppose there is one X who is Z or Y who has never sent an email, right? They took the username. Now everybody else is stuck with long usernames with 2001 and 2002 because of them, but they've never sent an email. They made an account, never sent a message. Now, I may be able to retrieve, there must be someone whose email I cannot retrieve. Not that one person. That person I don't even care, his email is empty, I know that, right? There's nothing to retrieve there. But the system says I cannot guarantee that I will be able to retrieve the email of everyone. Not just that one. Okay, that would be this statement the one I wrote earlier. Okay, let me go further. Take your time, think about it. If you have questions, you can ask next time or office hours or something. For every security breach, there is at least one mechanism that can detect the breach if and only if there is a process that has not been compromised. When you do software testing and system testing, you will see these kind of things a lot, okay? Program analysis and any big system testing, you have to be able to write this precisely and concisely and with the unambiguous interpretation by anyone even 100 years later, okay? So for every security breach, there is at least one mechanism that can detect that breach. So for every breach, there is a mechanism, at least one mechanism, maybe more than one, that can detect that. This statement is equal to this statement that there is a process which has not been compromised. If the whole system break down, all kind of processes are compromised, then there is no guarantee that every breach can be detected. Make sense? Okay, so I've given the translation. Oh, so there is no pause there? Okay, so I forgot. Do this. For every, so Y is breach, X is the mechanism, so the universe of discourse for X is the set of mechanisms, Y is the set of breaches, set of security breaches, and Z is the set of processes in the system, right? So this says, for any breach, there exists a mechanism, right? But you see this Z, this thing is free of Z. I can bring the Z here, right? If this mechanism can detect the breach, that is equal to, or if and only if Z, there is some process Z which has not been compromised. C means compromised and not C means not compromised. Does that make sense? So perhaps you can bring the third quantifiers here and it will make life slightly easier. Yeah. Yeah.
These can be interchanged, right?
Yes, you could swap them, yes. But that's why I had to put all the three variables on before starting the statement.
So would we be using like the same kind of structure in this structure to represent like for every
Yeah, so this is again because we want to train you, so we made up complicated example, confusing example, so you get trained. Generally, I'm a very big, very sensitive to using clear language, but you have to be trained, and at least you have to know that there's nothing to be scared of. Okay, yeah.
So do there exist Z वाला part है उसको right side पे भी लेके जा सकते
Yes, you can. Because you can. There is nothing wrong. I mean, you don't need Z here, right? But you cannot use Z here before after this sentence. Otherwise, it wouldn't just make sense, right? Z doesn't exist, and you started to use it.
हैं पिछले part में भी हम कर
Pichle maybe yes, we could do it. No, RY could, the second R, this, I told you there that this for all Y could come here.
But why didn't we put it like सबसे बाय?
किससे बाहर?
मतलब जिस तरह वहाँ पे सबसे बाय लिखा था ना जी तो वो बाय.
This will सबसे बाहर है ना. This part for all Z, this was called Q. We called it Q.
सर लेकिन next statement में आपने वो पहले कर दी बाद में.
This stands for something else. I mean, this is not that Z.
Sir that जो C में है
C में,
ये बात. तो ये तो अभी use ही नहीं हो रहा है. इस
you could write it here. Yes, this there exists Z can come here.
can we not write it out like why?
No, that will change the distance. That will change the meaning. That's just changing the quantifier order.
But aren't we not using that with dxy?
No, dxy has nothing to do with Z. So that would mean there is a fixed Z. You read the statement. There is something called parse tree. You know parsing tree? When you parse a sentence, I don't know, you should have learned it in grammar, parsing tree. You say there is a Z, there is a process. If that process is not compromised, then I can detect any breach. That doesn't say this thing. There is no such universal guaranteeing process. It says if at least one process is available, it may be different for each fault. Okay, it's not one. So you have to think. You should have learned this stuff in programming. You can't just switch the order of the loops, right? When things are nested, they have different meanings, right? Yeah, okay, everyone knows what is 2D array? 2D array. Do you know what is column measure processing of 2D array and row measure?
Yes.
Column measure and row measure, right? No? Okay. So, perhaps, where is Humaira? Could you note this, this thing also? Just take a picture and let me know. Maybe I will integrate them into slides and note something. Suppose I have a code like this. What will this print? In what order will the matrix, the 2D array A will be printed?
first row, second row.
It will first print, so let's say it will first print 1, 1, then 1, 2, then 1, 3. So this is called the row measure traversal of the array. Row 1, finish, then finish row 2, then start row 3 from end left to right and finish them, right? If I switch the order, if I write it like this, what happens? This becomes what's called a column measure. What will be the first cell printed? A11. What will be the second one? A21, right? Because I is changing. No, I is changing, so it will be 21. J is fixed now. It will be a column measure, right? These are totally different statements. Yes? Okay. So you can't just switch orders of stuff. Okay. There are at least 2 paths that connect every 2 distinct endpoints on the network. Yes? Sorry, please say it again. Yes, so let me just write it like this. see when you switch, I just switch the whole for loop, copy paste there, right? So this is nj, whatever the length of j is. This is ni, whatever the length of number of rows is. Okay? Do assignment 0, please. Okay. Did everyone did assignment 0? No? You did it? Really? Okay. Okay, there are at least 2 paths connecting every 2 distinct endpoints in the network. Now look at this statement. Just on the face value, it says if you give me any 2 points, I will show you 2 paths. Right? It doesn't mean that there are 2 paths that connect every 2 cities, right? It says between every 2 cities there are 2 paths. At least 2 paths, maybe more than 1, maybe more than 2, right? But between any 2 cities there are 2 options. Does it make sense? It doesn't say that there are 2 paths that connect every 2 cities, every 2 endpoints. Okay, so the way it's done here, for any 2 cities x and y, there exist 2 paths, at least 2 paths, which unequal paths, meaning you can't just mention one path twice and then assume there are 2 paths, right? So there are 2 paths, they are not, so the P2 is not equal to P1, that P1 connects xy and P2 also connect xy. Okay, so now if you switch this order, you bring, there exists P1, P2 before that, that would mean that there are these set of 2 paths, 2 roads that connect every 2 cities in Pakistan or in whatever, for any 2 computers in this system. That's not what we mean by this, right? Okay, let's do a few other translation from math to English. Yes? Is the statement clear? So what does the statement say? Can you say this in English? So this says that you give me any 2 endpoints, I'll show you 2 paths connecting them. Right? So you give me Lahore, Islamabad, I'll tell you, okay, GT Road and motorway, M2. Right? You give me Lahore, you give me whatever the city, Sialkot and Multan, I will show you, one is path through whatever, I don't even know where is Sialkot, but one is a path through Kabul and the other is a path through Karachi or something. There are 2 different paths. That's what this statement says. Now this is what it says here. There exist x and y. For all x and y, for any 2 cities, there are at least 2 paths. Okay. If I switch the order, if I bring this, there exists P1, P2 here and for all x, for all y there, this would mean that there are 2 roads, 2 paths that connect any 2 cities. That will be totally different, right? This will be not the same as what is meant by the black statement. Yes?
So if the question was there are at least 4 paths, it will change to 4 more variables, W, X, Y, Z. And then
there are 4 paths, there will be P1, P2, P3, P4.
at least 4 paths. How would this change?
Yeah, that's a good question. So if this statement says that there is a lot of robustness in the network, there are many options available. Even if one option is broken, the other will be available. Some more backup will be available. So that would be very simple thing. For any 2 cities, there are at least 4 roads, 4 paths, P1, P2, P3, P4, such that P1, P2, P3, P4 are distinct. I mean, P1 is not equal to P1, P2, P3, P4, P2 is not equal to P1, P3, P4, and P3 is not equal to P2, P1, P4, and so on, such that P1 connects xy, and P2 connects xy, and P3 connects xy, and P4 connects xy. So see if that will be just a simple mechanical extension of this statement. Yes, please.
For all x, for all y, the letter y, because that y is part of the quantifier.
What is aleda y?
For all y, not equals to x.
No, so you give me 2 cities, any 2 cities. This is what it says. Give me any 2 cities. Between these specific 2 cities, I will show you 2 paths, one P1 and one P2. So these x, y have to be the same.
So basically, मैं उसका नहीं कह रहा हूँ, जैसे x y not equals to x, अलग क्यों होना चाहिए? For all y not equal to x.
That's yes. So maybe you're right. That's y not equal to x. This y is like for all y other than x. That's what I'm saying in English. It says for every city, in every other city, there are at least 2 roads. You see that statement? For every city and every other city. Now you can say this for every 2 cities that are not equal. That's the same as what I said here earlier, right? For every city and every other city. Okay. So the next, now we're doing opposite, the English maths to English translation. Okay, quickly. The universe of discourse is real numbers for both variables x and y. What? Sorry?
X skip हुआ है.
There was question 30 and now 32.
That is in your assignment 0. For all x, there exists y, x plus y is equal to 0. Say this statement in Urdu, in English. Yes.
For every x when added to some y, it is equal to 0.
No, so that's even just, you just pronouncing it. Now don't do so robotic translation. Sorry?
Every x has an additive.
What is x? X is not a thing.
Every number has an additive inverse.
Yeah, that's.
Every number has an additive.
For every real number, there exists another real number such that is some.
When we add them, it gives me 0, right? So for every x is a thing, but that's written there. Every real number for every real number, there is another real number. Now this another has to be taken like lightly, okay? It's not unequal, right? For 0, it's exactly the same number 0. For every real number, there is a real number which when added to the number gives me 0, right? Our better translation is, because we know what does it mean that x plus y is 0, that every number there is an additive inverse, right? Again, I think we saw it last time for multiplication. There is an additive inverse, yeah. No, there is an additive identity. No, what? For all x, there exists y such that x plus y is 0. So it's inverse, yeah, it's inverse. For all x, there exists y, yes. So every number has a additive inverse. Now, please in your mind change this order of these 2 quantifiers and see what does it mean. If you say there is a y, there is a magical number y, which when added to anything gives me 0. That's not true, right? Doesn't exist any such number, but it definitely is very different than this statement, the blue statement, right? I don't do anything else except for change the order of the 2 quantifiers and the variables, right? That's it. There is a magical number which when added to anything gives me 0. That's just not true, right? It's true for multiplication. Is this true for this multiplication? If I say there exists y such that for all x, x times y is equal to 0, what is that called? What is that called? If the number is 0, that's called some kind of multiplicative identity, or it's not multiplicative identity. Identity means you get the same number. This is like just a crusher, right? It's a multiplicative crusher, right? It just crushes the x number, it makes it disappear, right? So, but that's a different statement than this, right? Sorry? Okay, so there exists an x for all y, x plus y equals y. What is this? Please say it quickly. There exists such a number x, which when added to any number y gives me y back. Translation. I'm not asking you for examples or truth or falsehood of this statement. Can you translate?
All numbers have one additive identity.
He begin the statement with all numbers, then it's a big this thing. There is, that's what he starts. There is.
There is a number when added to any number it gives the same number back.
Yeah. So there is an additive identity that gives the same number back. Is this identity it's clear? There is a number which doesn't change any number by addition. Okay? It doesn't increment or decrement any number. Okay? And that number is 0, so it's a true statement. Again, if you change this order of this statement, the things will just become very different. Yes?
Selection, you said you should avoid trying to write there exists and for all when you're translating.
Okay, so there is an additive identity. Okay? That's right. This existence is always a tricky question. Yeah. Okay, so for all x, there exists y such that if x is not equal to 0, then x times y equals 1. Yes? Yeah, for every real number x. Yes? Yeah, every number which is not 0 has another number which when multiplied gives me 1, right? So every non-zero number has a multiplicative inverse, okay, or the reciprocal of every non-real number exists, right? Forgive me for using exist again. Okay. Make sense? Okay, for there exists an x for all y, x y equals y. There is a multiplicative identity in the world, right? Among the real numbers, a set of real numbers have a multiplicative identity, okay? Or this is in the group of real numbers actually has a multiplicative. Okay, so now how would you negate nested quantified statement? Recall this. How do you negate universal quantified statement, one quantifier? You apply kind of the De Morgan's law. And just by our understanding of for all x, p of x, when is this true? When p is true for all x's. So what's the negative of this? Well, at least for some x, p is not true. Okay? So the negation of not for all x, p of x is equal to there exists x, not p of x. Right? I told you, think of it as negation goes inside and the quantifier flips. Right? Similarly for the other thing, it's just an application of De Morgan's law. Okay, so how would you negate nested quantifier? Exactly the same way, right? You think of this is what we did here. There is a whole mess of this thing. You think of this is a quantifier, is a one statement, and now we have for all x q. What is the negation of this? There exists x not q, and then you apply not q to what is not q. You just iteratively apply. You take it inside the nest, the negation. Yes.
इसका mathematical proof क्या होगा?
किसका mathematical proof?
Equivalent आपने लिखा हुआ है कि negation अगर
This we talked about it in very detail. I gave you the if universe of discourse is finite, then it is the it follows from De Morgan's law, okay, and this is how we defined it. When is for all x p of x true? When is for all x p of x true?
there is no x for which p of x is false.
No, for all x p of x. Yeah, okay. There is no x for which p is false. Okay, that's for p is true for all x, right? I want the negative of this, the negation of this, meaning I want a statement which is false when this is true and true when this is false, right? So when is for all x p of x false? Oh, so you wanted mathematical proof, okay?
Yeah.
So when is this true? Quickly.
P of x y intersection P of x.
So when is this true? For all x p of x, not the negation, for all x p of x.
When there doesn't exist an x for which
Yeah, so why do you have to say ulta? Just say it when for every x p is true. So he said if there is no x for which p is false. I mean, why do you have to say that? When is it true? When p is true for every x. When is this true? Okay, when is this false for all x p of x?
when there is some x for which p of x.
P is false, right? For which p is false. Okay, there is some x for which p is false, right? The property p is false. Now look at this statement. When is this true?
Right, Willie?
Yes. It says when there is some x for which p is false, right? That's exactly what you told me here when this is false.
इसे वो तो वैसे
Not वैसे, it's exactly
intuitive
true.
proof है, कोई comparative
There's no
mathematics.
intuitive, that's exactly the proof. Okay, that's exactly the proof. I mean, there's no proof, it's just a different language, right? It's not a, there's no new thing in math, right? It's just saying the same thing more precisely and more better way. Okay, so this you will do this. How would you quantify and negate this nested quantified statement? Quickly.
There exists an x for all y that.
No. Slow. Give step by step. Iterative application of these principles. Just apply what I did here. Just do it one quantifier at a time. Quickly. One quantifier at a time. There exists an x in the negation of the remaining. Right? There exists an x, the negation of the remaining inside quantified statement. Right? How would you do this now? This inner part? There exists an x will go exactly as it is. Quantifier flips, negation goes inside, right? Is this clear? Nothing fancy, exactly the same thing as we did, just like when we are taught multiplication of three numbers, we say, okay, forget about the last two, let's call them one number, you multiply one number with this thing, right? It's associative law of multiplication, they are taught to us like this, right? And this is exactly that thing. How would you negate this one? Quickly give me the first step. For all x, negation of for all y, p of xy, right? And then for all x there exists y. Okay? How would you negate this one? Yeah, there exists x, negation of for all y, and this one. And this one, give me the last final answer. What? You will. Yes. You will negate all the quantifiers. Generally, when I say negate the statement, doesn't mean that you say, like you remember last time I had an example and I said, negate this statement. But you cannot say that it is not the case that this statement is true. That's negation, correct? Negation. But when I ask you, I want you to simplify the thing fully. Right? So if I tell you what's the negative of 5, you can't just say it's a negative of 5. Right? I want to say here that, see, what's the inverse of 5? Right? What's the inverse of 5? So what's the inverse of 5? You can't just say it's the reciprocal of 5, right? I mean, you tell me 0.2, right? Is it clear? I want to know this is 0.2 or something. So here you can, that will be correct if you don't negate the remaining proposition, but it's not complete. It doesn't make life simpler. Generally, it's a more precise statement for such questions in homeworks and problems set and exams would be, write a negation or negate this statement. There should not be any not negation sign in front of any quantifier. Right? That's for those people who haven't done assignment 0. You hopefully have done it. So I would say when I ask you to negate the statement, that means there should not be any negation of, there should not be any not sign before any quantifier. Okay. So this is how you negate these things. That's it. So you can do, this is not an ICP, but do this example. X teaches course Y in LUMSx. Right, that's the predicate, and now I'm making a statement. For every course, there is an instructor teaching it. Right, most probably a true statement. Otherwise, course perhaps would not be defined unless it's a self-taught course or something. Translate it into a quantified expression. Quickly, translate it into a quantified expression. What is Y? What is X? For every course, there is an instructor. So for all courses Y, for every Y in the course set, there exists a X in among the instructors who such that P of XY, right? Or P of YX, P of X. Now negate the quantified expression in math. For all y? No, for there exists y for all x not p of xy. Now translate that quantified expression back to English.
There exists a course that none of the teachers are teaching. For all teachers are not teaching it.
That no course is teaching it, right? And that will be the negation of the given statement. For every course there is some instructor. Now what you told me, shall I do it on the board? So for all y, for all courses y, let me just write it, for all C is a course, there exists a professor, no, there exists an instructor such that this I don't know, what does this mean? Or I see, I guess. For every course, there is some instructor who teaches it, right? Now, if I negate it, this will be yes. Now say it in English. There exists some course that I checked with every professor, they are not teaching it, right? So no one is teaching it. And that's the negative of this statement, right? Some course is not being taught by anyone. That's the negative of this course. So a set is an unordered collection of objects, right? An unordered collection of objects. Every word is important: collection, objects, unordered, and set, right? Set is the name we give to these creatures, and this is the first discrete structure we are studying, and we'll build upon it extensively, right? Your whole data structures course is just extension of sets, some filtering, some special types of sets with some special properties, and when we do graphs, there will be special sets. We talk about groups, we talk about the whole abstract algebra. The first word, it begins with groups, fields, rings. Everything is just a set with certain other specs, right? There is operations, some other. When we do data structures, arrays, list, binary search trees, dictionaries, hash functions, hash tables, red-black trees, AVL trees, B trees, Fibonacci heaps, queues, stacks, every word is just should begin and does begin with the word set, okay? But with slightly more thing. Ever heard of data science? What's the first word we hear in the word data science? Data? Huh? Data set. That's the word you should hear. Data set. You're given a data set, you want to draw, you're given a set of data, you want to draw information out of it, right? You want to learn from it, you want to make sense of it, you want to visualize it, or whatever you do. So the set is that type of a word, right? You can't say anything about, you can't talk about stuff without the word set. Okay, so here is a set of objects, unordered collection of objects, 1, 2, A, B, Fred, LUMSx, right? Is it a set? Yes, it's a collection of objects. Some objects are numbers, some objects are characters, some objects are people, some are universities or whatever. We never said anything about the types of objects. It's any collection of it. The next set, which we call N, is 0, 1, 2, 3 is natural numbers, right? The next set is B, is the set of all professor in LUMSx, right? Next one is B, X such that X is a professor at LUMSx, right? That's another set. When I said it's unordered collection, meaning order is just not important. 1, 2, 3 is exactly the same set as 2, 3, 1, right? You no matter how you write it, it's the same set, right? In whatever order you write it, it's also unordered collection of objects. This is an important thing. Later tomorrow we'll mention this word called multiset. Multisets are those where repetitions also are important, and they do matter. Here it doesn't, right? A repetition doesn't matter. So 1, 2, 2, 2, 3 is the same as 1, 2, 3. Why? Because this object 2 is repeated 3 times, the repetitions don't count. Okay, so this is unordered collection, and these two words you should understand very, very clearly. Okay, if you've worked with C++ or Java or Python or some, there is things called arrays there, right? Arrays are just a slightly restrictive version of sets, and they have, generally speaking, we require them to have all elements of the same type. So for example, this set generally won't qualify to be an array, right? Because an array have to have all integers or all reals or characters, all structures, all objects, all whatever data type you have. In C, this may not be allowed to be an array, right? So it's somewhat similar to this. Plus, in arrays, order is also important. There is a first element and the second element. Those are more closer to what we are going to study later, sequences. Yes?
Does the repetition not qualify to be a set, or is it a set?
No, it is a set. It is a set. So I didn't say it is not a set. I said this set is the same as this set, right? You know the notation of sets. The way we write it is curly braces. In LaTeX, you will write it is slash, this curly brace begin and slash end this thing with this slash. And okay, everything done. That's it. That's all we need to know about sets, right? About definition. The rest we will just, this just the details or just more explanation of the slide. Okay, this is the notation we are going to use. We will just generally denote sets with the what is it called, uppercase English letter, or we'll give them names, bigger name, set of professors or something like this. These objects are called the elements or members of the set, right? The notation for that is x in A. This is how it's pronounced, x in A. X is an element of A. In LaTeX, you will write it is x slash in slash in A. That will give you this type of thing, right? X is an element of A. Sometimes we say A contains the element X, right? The set A contains the element X. And so you write it is slash ni slash ni will give you this notation in LaTeX. This is how it's pronounced, right? So depending on the need, we will use this thing, okay? Now, sets can be described many different ways, okay? So I can describe the set of TAs for this course by just giving you their names or their roll numbers or their pictures or their whatever, right? So some kind of identity that uniquely identify these TAs, I will give them your roll number, and that's how I can describe the sets, right? So this is called set description by tabulating all the elements, by listing all the elements of the set, right? A listing doesn't have to be for infinite sets, for sets which have too many elements. We could write, we can use some kind of notation for this, that 1, 0, 1, 2, 3, and that means the rest, all the rest of the elements. So set of natural numbers 0, 1, 2, 3, 4, we know what we mean by this. Slash L dots will give you this thing, slash C dots will give you these dots slightly on the vertically aligned, and other stuff. Set can also be described by just give you some English description of it. So if I say the set of TAs for CS210 in fall 2023, that will give you exactly the same set, right? So it's not important that you write it in a particular way. That's just a notation we use that makes things very clear. The set of all students in CS210. It's a full description of all of your roll numbers in a list, right? The whole Zambil record is going to be exactly the same set. So I can give you all the Zambil record printed, or I can just describe it like this, right? The set of all professor in LUMSx, the set B I saw earlier. We can generally we describe sets, and that's how we identify, work with sets, is by giving you what's called a membership predicate, right? A set is a collection of objects. So I just give you a predicate which just tells me which element is in the set and which is not in the set. So if the predicate, the property of being a membership predicate, the property of being a member in the set is true, then that is an element of the set, it's a member of the set. If it is not true, then it is not a member of the set. Okay, that's why we study predicates a lot, and then we'll see a lot of this. So look at this set. B, this set, the set of all professor in LUMS. This is exactly the same set is given here. X, all objects in the universe of discourse, the set of people, the set of cats, the set of whatever, X, for which if this predicate is true, then that X belongs to this set. Otherwise, it doesn't belong to the set. Okay, so we can say, does Pythagoras belongs to the set B? No, why not? Because Pythagoras is not a professor at LUMS, right? So this predicate is true, is false for Pythagoras, right? So we know who is in, who is out. Okay, so this gives us a membership criterion. These are like kind of these predicates. Membership predicate is like the gatekeeper of these sets, right? They allow some people in and others not in. What is this? C. X is a natural number such that X is bigger than 10. Can you give me some elements of C? 10, 11, 12, 13, 14, right? Not 10. How about 14.3? Yeah, so there are actually in different ways written, and I'm going to give you many different ways to describe sets. These are actually a compound predicate, or more than one condition about X. One is that it has to be an element of the natural sets, which I have described above, and one is that it has to be bigger than 10. So both of these predicates have to be true for this, or both of the conjunction of these predicates have to be true. Okay, so that's why 14.5 is not here. That's why negative 17 is not here, right? And that's why 10 is not here, or 9 is not here. Okay, for different reasons, some are here, some are not there, right? So you see what set can be described in 3 different ways, right? At least 3 different ways. So let's just do a few examples. So I'm going to ask you to giving you some sets, and you are supposed to write the first 5 or 6 or some number of elements, depending on how quickly you can do some calculations for these sets. Okay. So look at the set A. X such that X is even in a perfect square. So the universe of discourse is basically integers or real numbers or something. Give me perfect square. Perfect square are those numbers, perfect numbers are those numbers whose square root is an integer, right? Or which can be written as the square of 2 integers, the square of n integer. Give me 2 is a perfect square. Is 2 in the set A? Why not? Is 1 in the set A? Set 1 is a perfect square, but it's not even. 3 is not even, right? 4 is a perfect square, it's a square of 2, right? And it's an even integer. 5, 6, 7, 8, 10. 10 is even? Not, right? The next even integer is 16, which is perfect square. Then 36, 25, no, 25 is not, right? 36 and then 64 and then 100, right? So that's 5. You know what is the set A, right? It's given there, it's even numbers who are also squares, right? Perfect squares. Got it? These are the numbers that can be written as a area of a square with integral coordinates, integral lengths, right? Okay, the set B. B is a set of those x's such that x plus 1 is a multiple of 4. So now is 1 part of the set B? Why not? Because 1 plus 1 is not a multiple of 4. Is 2 part of the set B? 3 part of the set B? Yes, 3 is part of the set B. 4, 5, 6, 7. 7 is part of the set B because 7 plus 1 is a multiple of 4. You could go the other direction. Is negative 3 part of the set? Negative 3 is part of the set. Is negative 4? Negative 5? Negative 5 is part of the set, right? Because negative 5 plus 1, 4 is a multiple of 4, right? And then similarly 11 is a an element of this set, and then 15, and then 19, and so on. Right? Is it clear? You guys please pay attention to me. Okay, so set C, x is a rational number. You know it's a rational number, right? That can be written as a integer divided by another non-zero integer, right? Those are called rational numbers. Such that the square of that rational number is less than 2, right? Is 1 a rational number? Is 1 part of the set C? Yes, because 1 squared is less than 2, right? So it will be there. Is 2 a rational number? Is 2 part of the set? Why? Because 2 squared is bigger than 2, right? So similarly 1.5 is a rational number. Which is part of this set? It's not part of this set because the square of 1.5 is bigger than 2, right? Is 1.2 an element of this set? 1.2 is a rational number. What's the square of 1.2? 1.44, that's less than 2, right? So it will be part of this set. Can you give me some more? Just think about it and write something, right? Sorry?
1 by square root 5. 1 by square root 6.
1 point what?
1 by square root 5.
1 divided by square root 5.
1 by square root 6.
Okay, 1 divided by... Whatever you want, I didn't stop you, but you know how to make the set, right? You see how I gave you membership predicates, right? Let's see the set x squared such that x is even. Give me a few elements of those things. 4, why 4? Because 2 is even, 2 squared is 4, so we write it. Then 6 is not a square. 36, yes. 64, 16, 4 is even, 4 squared should go there, right? 16, 36, 64 and 100, right? Okay, so y is equal to 4x minus 1 such that x is an integer. The set z, this stands for integers, x in z, give me any integer and then 4x minus 1, yes. We'll come to that. Give me the elements of y. Give me some elements of y. 2 is an element of this set. Why not? Why is 2 not an element of this set? So you have to just write, yes.
Smallest possible would be 3 because 4 for x1.
No, it could be negative. Negative 3 is part of it. Negative 5 is an element of this. Negative 3 is an element of this because 3 is an integer. And 4 into 3, no, sorry, what did I say? 1 is an integer, 4 into 1 minus 1 is 3, so 3 will go there. 2 is an integer, 4 into 2, 8 minus 1, 7 will go there. 3 is an integer, so 4 into 3, 12 minus 1, 11 is there. 14, 15 is there, 19 is there, right? And the set z, the square root of x such that x is less than 2. The square root of x such that x is less than 2, right? Can you think of a number less than 2? 1. What is the square root of 1? 1 is less than 2, right? The square root of 1 is what? 1. And maybe negative 1 also. It depends how you define square root. And is 1.1 less than 2? What is the square root of 1.1? Right? 1. Whatever. Is 1.44 less than 1? Less than 2? What's the square root of 1.44? 1.2, right? So all of these integer, these real numbers will go here, right? In this set. Do you see that the set A is exactly the same as the set D? The set X, right? The set B is exactly the same as the set Y. That's what you said, right? Somebody said there something. Yes? You asked that question, right? The set C is the same as set Z. So these are just 3 sets, each given in 2 different ways, described in 2 different ways, right? That's where we studied, when we studied logical equivalence, the equivalence of two propositions or two predicates. That's why it's important. This is now what we can say is that this propositions coming from this thing is exactly the same as the proposition coming from this thing, right? That x plus 1 is a multiple of 4 is exactly the same as that is exactly the same as 4x minus 1 when x is an integer, right? And x is an integer. These two properties are exactly the same but worded very differently. Okay, you understand that? Some of the sets that we very frequently are going to use and do use in mathematics are these given here. The set of natural numbers 0, 1, 2, 3, 4, 5, 6. The set of z is the set of all integers, negatives, zeros and positives integers. Z plus is the set of positive integers. Q is the set of rational numbers given as, can be written as an integer divided by a non-zero integer. Any number that can you write as an integer divided by a non-zero integer, that is called a rational number, right? The set of real numbers, numbers that occur in reality, right? Real numbers. Int in C++ and Java and other data types in different programming languages, int is actually the set of those integers that can be expressed within 32 bits or 64 bits depending on the word size of your system, okay, or 16 bits. Double is a set of those real numbers that can be expressed within 64 bits, okay, it's a set. Double is a set. And the way when you assign a number to double which is not this thing, the compiler actually does a membership testing. If the number, some x assign some number, if that number is not in the set double, then they will give you a compile time error, right? What is it called? Type mismatch or some kind of error, you'll get that. Okay, a very important concept is that of the empty set. Okay, an empty set is a well-defined set. It's denoted by this symbol phi or the symbol, this symbol. Generally I will use this one. You can write it in LaTeX, you write slash empty set, you will get that symbol. It's not phi but it's close, similar to that. The slash empty set, this is a set which has how many elements? 0 elements, right? A set could contain other set. Okay, set could contain other sets. So this is a set. How many elements are there in this set? There are 3 elements in this set, right? One is a set of with 2 elements, the other is a set with 2 elements, and the other is a set with 1 element, right? But there are 3 elements or members of this set A, right? Set could contain set and other sets, other non-set elements, right? This could be any mixture of this thing. Generally in the mathematics literature, these things are called a family of sets or a collection of sets. Family of sets just to set of sets or becomes like a little bit cumbersome to pronounce. So we say it's a family of sets, okay? But nonetheless is a well-defined set and everything. So what is the difference between this A and this A? Because this one contains some set and some non-set elements, objects. This one contains all the objects in the set, the second A is just sets, right? So this is one a common thing that people tell you that, what are you thinking about, right? Or, yeah, so this is the correct way is that they are thinking about empty set when they tell you we don't think about nothing, okay? Okay, set equality. 2 sets are equal if they have the same elements. Okay, 2 sets are equal. Remember equality of propositions, right? The if and only if thing. Now we have to come to that, right? Similarity gate, if you remember I used the word there, the equality gates. 2 sets are equal if the membership predicates for each one there is if and only if between them, right? If they are logically equivalent. So set A is equal to B if for any element x, x is in A if and only if x is in B, right? How would you say this in Urdu with the set A is B? Any element that is in A is also in B. That is if A then B, right? If x is in A then x is in B. And If x is in B, then x is in A. That's the two ifs, right? One is the converse of the other. If x is in A implies x is in B, and the converse of it gives us if and only if, and that's the definition. Okay, with two sets being equal. I'm going to give you at least 3 more definitions of this equality of the sets. It's a very important thing. Just like we did logical equivalence, we are going to do set equivalence substantially in substantial depth. Okay, is this set 3, 1, 3, 1, negative 3 and 9 equal to the set negative 3, 1, 3, 9, right? Yes. Just visually, why are this equal? Because order doesn't matter, right? But let's see, we have a good definition of this. We have a predicate here, a quantified predicates, and let's see if that is true. Let's see, what is the value of this predicate for x equals 5? What is the value of this predicate? Is this predicate true for x equals 5? For x equals 5, this is not true. What's the value of 5 in A? What is the value, what is the truth value of the proposition 5 in A? False. What is the truth value of the proposition 5 in B? False. What is false if and only if false? True, right? When both are false, this is true, or when both are true, right? Is this predicate true for x equals 3? For x equals 3, both are true. For x equals 9, both are true, right? For x equals 9.5, both are false. So this statement is true, right? That means A equals B. A equals B means that if and only if for all x in A, if and only if x in B is true. Is this clear? And you can just do we know this statement, these two are true, and we saw that it's just false. Here is a set A, P, Q, R, S, and B, R, Q, S. Are they equal? Why not? Visually? P is in A, but it is not in B, right? Let's go to the if and only if formula. Is this for all x in A, x in B, is it true for Z? If I plug in, the x is their variable, not a letter, okay? If I plug in the value Z for x, is this statement true? Is it true or false? It's true, right? Because Z is not in A, Z in A is false, and Z in B is false, so this is true, right? Is it true for Q? So Q is in A, true, and Q is in B is true, so true, if and only if true is also a true statement. But is it true for all x? For what is a counterexample? When you say for all x statement is not true, if you say a universally quantified statement is not true, what do you need? You need a counterexample. What is a counterexample here? P. P in A is true. So, okay, the complement of a set A is the set of those elements that are not in A. Please pay attention to me. The complement of a set A is the set of those objects which are not in A will go to the complement of a set A, okay? So is Q, everyone knows the rational numbers, right? Any number that can be written as an integer divided by another integer that is not 0 is called a rational number. So what will be the complement of the rational numbers? Irrational numbers, right? So what are those? Is square root of 2 a rational number? We will prove it later. This is a very good story associated with it that I will tell you. Is pi a rational number? Pi is not a rational number, okay? It cannot be written as an integer divided by another integer. Is e the base of natural log, the Euler constant, is that a rational number? It's not a rational number, right? Is cat a rational number? Is cat a rational number? Is calculus a rational number? So what's wrong with this? What's wrong with this definition of complement of the set? We said any number that is not in Q, the set of elements not in Q will go to complement. Yeah, we need to say what's called the universal set, right? Just like the universe of discourse, Last time when we talked about predicates, we said we need a specific universe of discourse, otherwise it doesn't make sense. So the correct definition of the complement of a set A is denoted by a bar over this is the set of those elements in the universe of discourse, in the universal set, which is not in A, okay? So this is the definition. This is how you can picture it. If you have this universal set called, let's say I pictured it as green, there is a set A, anything which is white, anything that is purely in green and not in white is called the complement of the set A, okay? Okay, last thing I want to tell you, go home and think about it. It's called the Barber's Paradox. There is a certain town, there is a male barber, there is exactly one male barber, who the law or the rule or the fact is that this barber shaves all those people and only those people who do not shave themselves, right? So these some men who shave themselves, they are not shaved by the barber. Some men who do not shave themselves, they are shaved by the barber, right? There is no other barber, there is no other possibilities, okay? Let's see what happens. The question is, does the barber shave themselves?
If he does, then he doesn't, and if he doesn't, then he does.
If the barber shave himself, then he shouldn't shave himself, because the rule says if anybody who shaves themselves is not shaved by the barber. And if the barber does not shave themselves, then the rule says they should be shaved by. What is this? So you can do this kind of analysis, and now you know enough logic that you can do this analysis, right? If B is in M, then B should not be in M, and if B is not in M, then B should be in M, right?